Hey everyone, Michael Unger here with the Science Fair Foundation BC. I am here in my kitchen on a very blustery day on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh. Welcome everyone to a STEM workshop. Today's topic, as you can see, understanding the scientific method. This is a great one. We are starting the school year. We are starting Science Fair season, and all of you joining here may be thinking about joining science fairs. Maybe you've already started to get involved in some projects, and we are going to lay that foundation for some of those projects with the scientific method. And today we've got a couple amazing speakers that are going to lead us through this method. First, Anne-Marie Simard, who is a former science fair participant herself, member of the Vancouver Island Regional Science Fair Committee, and a science teacher. Hi, Anne-Marie.
Hello.
So, former science fair participant, and you're now on the committee. You were a science fair junkie, I guess.
Yeah, something like that. I guess I've been involved some way in science fair since 2003. So it's been a while now, and it's kind of part of my life. And now I teach sciences in high school, and I help my students create science fair projects, but I also help out as a volunteer in the community to organize science fair and help students and mentor them so that they can make great science fair project every year.
Yeah. So, what is it about science fairs that you keep coming back to?
You know what? It's interesting. I guess when I was in high school, I wasn't necessarily like the most sporty person, and science fair was kind of my niche. And I started really enjoying meeting people of my age that were also really interested in science. And I made lots of friends through science fair that are still my friends like today as adults that I met when I was in high school. So it was a bit of my niche, and I just found my place and my people, and I really like to learn and challenge myself. So science fair was for me the way to do that at that time. Yeah, and it just stuck with me after that.
Awesome. Well, thank you so much for joining us, Anne-Marie. We're going to, you're going to lead us through the second part of the scientific method. But to lead us to the first part, we have Dr. Greg Beaulieu, the former head judge of the Vancouver Island Regional Science Fair and an associate teaching professor and undergraduate advisor at the Department of Biology at the University of Victoria. Hi, Greg. How are you?
Good. Nice to be here.
Thanks, Greg. So what is it about the scientific method that you find so integral to this process of doing science, and specifically a science fair project?
Well, when you get really involved in science, something very strange happens. You start finding the methods more interesting than the results. And so if you think about, I don't know if you've heard about this gravity wave detector, there are twin detectors in Louisiana and Washington State. And they detected gravity waves a few years ago, and they have to detect oscillations less than the diameter of a proton. And so these are the very, very small effects that gravity waves have. And you can't help wondering, how on earth do they do that? I mean, it's interesting there are gravity waves, but it's more interesting that we can actually know there are gravity waves. And I remember when I was in school many years ago, I learned about cloning, and you can clone a gene and bacteria and so on. And I remember feeling, I have to know how that's done. Like it's like I couldn't go to sleep that night until I found out how it's done. I had to do a PhD to find out how it's done. But there is something about methods that are surprisingly attractive and interesting when you start getting into science. And I think that's why popular science sometimes, it leaves out a lot of these methods, and people's interests are going to differ, but it's how we know things that really is a more interesting question to me than actually what we know.
Yeah. So, Anne-Marie, if we were just to define what we're talking about here when we say the scientific method, I think I remember from when I was going to school, it's described to me as sort of like a messy sort of trial and error. How would we define scientific method for people that need to know about it?
Yeah, I think for me, the scientific method is a series of steps that you can use to guide yourself through discovering something or building an experiment or trying to answer a question. And I think a lot of the time we teach the scientific method as this linear path that's just like, here's the step you have to take, and then you're going to take the second one, and eventually you'll get to your results. But I think we have to see this as well a bit as a cycle. It's never it doesn't end. Like you never reach a final point to a method. Like, yes, you're going to have done a few experiments, but you're always going to be able to improve, to add to it. Sometimes you're going to try something, it's not going to work. You're going to come back, try differently, and you're going to tweak. And, not so much trial and error, but I would say testing with a proper foundation and ideas of why you are going to test something in a specific way in the first place. But I think it's important to realize that this is a series of steps that's going to be flexible, but there is a core understanding to it first, and there's a core way to do it to make sure that I would say that you don't forget any important steps. But there's a lot of back and forth.
Yeah. So Greg, as we talk about this, and you've described sort of with the example of LIGO, using the scientific method, but why would anyone need it? Like, why would kids now, like going into their science fair projects, why would they want to use the scientific method?
Well, one way I think of it very generally is that science is better than scientists. Okay, scientists are just people. And in my experience, they're mostly excellent people, but they're people. They have the same biases, and they can fool themselves, and the same stupidities, and they have brain farts and so on, like everybody else. But in science, all those imperfections and frailties are kind of ironed out. And what this gives you is enormous power in answering questions. If you just try to answer a certain question about the world without using the scientific method, maybe you're very observant, you might come up with an interesting answer, but there'd be more human variation person to person in their answers. And a lot of their answers would derive from expectation, from confirmation bias, from self-deception. But the scientific method has been built around human frailty. It's sort of an encasing of human frailty. And it didn't come out of the head of Zeus 2,000 years ago. I mean, it was put together over a long time by people who said, oh, well, maybe people can introduce bias into this example, into this situation. Here's how we eliminate that bias. And so if you look at clinical trials, for example, done 100 years ago, 150 years ago, they're done very differently than they are today, simply because we now recognize certain sources of human imperfections that can affect the results. So the scientific method gives you power that you might not have as an individual human being. It allows you to get good answers to questions that would otherwise not be accessible.
So to kind of use the video game analogy, it's kind of like a power up for your scientific powers. It's like once you've got that scientific method sword, and now you've got a really good piece of equipment that you can go and try to tackle a problem. Anne-Marie, why don't we go through some of the steps that we're talking about here when we say the scientific method?
Yeah, absolutely. So I think, like I said before, this is, we have a line to follow here in terms of the general steps, the core steps that we can follow. But just remember that at any point throughout this series of steps, if you realize that you forgot something or something's not going the way you thought it was going to be, or you made a mistake, you can always come back, backtrack a little bit and adjust and go from there again. The first thing to start with, it would be to ask a question. So once you have an interest or you're curious about something, you would like to know how something is working, or what would happen if I tried this, but I changed this instead and I did something slightly different, what would happen? You have to start with something. And you want to make sure that your question, especially if you're thinking, oh, eventually I'm going to do a science project with this, you want to have a question that's specific enough so that you're going to have a good line to follow there. If your question is a bit too vague, you're probably going to struggle to figure out exactly which way you're going to be doing. And then you're going to want to be doing a bit of research about your topic. And we're actually going to walk you through all of these steps one by one right afterwards. You want to see a bit what's been done before. What do you already know about the topic? And then you're going to figure out a prediction, or what do you think is going to happen? What's your objective or your main goal looking forward for this experiment? Greg, did you want to look over the next ones?
Sure. Well, you do make a guess as to what the answer to your question might be, and it doesn't have to be correct. It has to be fruitful. Okay, so you're not necessarily trying to be right, although it'd be nice if you were right. What you're doing in forming a hypothesis is using that hypothesis to direct an experiment. You're going to test that hypothesis. So forget about whether it's true or not. You're going to test whether it's true, and a good hypothesis is testable. A bad hypothesis is not. So you do your experiment. You look at the results. Analyzing the results will be a topic for a later workshop. It's not always straightforward, not always simple. Sometimes the answer emerges from quite a lot of statistical analysis. So there might be this amorphous cloud of results. The answer is hiding in there somewhere, and it's not obvious what it is. But in any case, you get your results, and then you go back. Do these results confirm your hypothesis? We tend to avoid the word prove. You don't hear the word prove in science much. Science is open-ended, so every result is provisional. So instead we use the word confidence. Perhaps our results give us more confidence that the hypothesis is correct, or perhaps they contradict the hypothesis and show that it needs to be either thrown out or at least modified in some way. And as Anne-Marie said, Anne-Marie talked about science being cyclic. Every answer suggests another question. So this is just a never-ending cycle of question and hypothesis and results and answers, another question.
It's interesting that you say that scientists don't use the word prove. I think that if you watch TV, if you watch any courtroom dramas, you hear lawyers, trying to prove point, and they're also using science often, and they often use that word, we're going to prove, innocence or something like that. But that's not quite how a scientist approaches, trying to tackle a problem, right?
Yeah, I think it's okay to use the word prove as long as you understand it in the legal sense, proof beyond a reasonable doubt.
Right.
Now, lawyers and courts have to come up with a certain definitive conclusion at a certain time because they're deciding on the fate of some defendant. So when something is proven, then that's the end point of the deliberations, and the defendant is either released or sentenced. Right. So there's no end point like that in science. It just goes on and on and on. So there's no need to use the word proof. Right. Yeah.
So let's get into our demonstration. So for everyone that got signed up for this workshop, you would have been distributed a worksheet, a list of materials before this session. We're going to put a link in our chat if you don't have access to that right now, so you can follow along. If you've already got your materials, we're going to show them live as well. So let's start with you, Greg, and let's start with our first step of our experiment right there at step number 1 of asking a question.
Okay, well, the person here noticed that there's some air inside a hard-boiled egg. Why doesn't my egg float in water? Now, you might think this is just surpassingly silly. I mean, who cares? A lot of interesting science can derive from such apparently trivial questions. One way I like to put it is, in science, quite often big things come in small packages. So you can ask an apparently trivial question and actually get kind of an interesting answer from this trivial question. Now this particular question about an egg floating in water happens to have some relevance to me. I didn't make up this experiment, but one of the first questions about the world I asked myself when I was a very young kid is, I'd throw a rock in water and it would sink. And then, I knew about ships. Ships would float on the water. How can a ship float and a rock sink? Ships weigh more than rocks. I didn't know about density, but anyway, that is meaningful to me. And as we go along, we're going to, and this will be especially true when Anne-Marie starts to talk, we will see a lot of specificity, a lot of fussiness about measurement and counting and so on. A lot of accountancy, I guess you could say. And you might think this is overly fussy, overly persnickety, which is one of my favorite words in the English language, but there's a reason for that. And the reason is, and this is critical in science, is repeatability. And to illustrate what I mean, I'll contrast a couple of situations. Suppose you're a guitarist and you write a piece of music, and you start it on a Friday evening and you finish it on Sunday at lunchtime, and then you try to play it straight through. It's a very complicated piece of music you've written. It's challenging for you. It takes you about 24 hours, but finally you learn how to play this music without making a mistake. So you show it to your guitar playing friends, and they like the music. They love it when you play it for them. But try as they might, they can't learn the piece. They can get partway through and then they make a mistake. And, someone tells you that he practiced for a week and he couldn't learn it. What does that mean? It means you're a terrific guitarist. Now, suppose you're a scientist and you ask a question and you form a hypothesis and you test it and get some results, and other people are interested, but they can't repeat the results. You're the only person who can do this experiment. Does that mean you're a terrific scientist? No, it means you're a lousy scientist. It might mean you're a fraudulent scientist. You could be making up your results. This is one way fraud is detected in science, lack of repeatability. So all this detail and specificity, especially that Anne-Marie will be talking about, has a purpose, and that purpose is summarized by one word: repeatability. So we asked this question, and what do we need to know just before we do anything in the lab? What do we need to know to answer this question? What makes an object float in water? So Michael, maybe you can tell us a few things about what we might want to research online or in books.
Yeah, well, I think that, we're talking about an egg. So I think we'd want to know about the composition of an egg. We'd want to know a little bit about what's inside of it, its density, and perhaps the different kinds of eggs that we might be able to choose as well. I'm a vegetarian myself, so this would be like, I don't buy eggs, so I don't know what are the kinds of eggs that you would buy out there, but that might be some questions that you might want to investigate.
Sure. Well, the reason you're doing this, again, it's you're not an individual. You're an individual mind, but you're participating in a social activity. And this social activity might consist of people you work with or just people in general. But there are going to be people who have determined things in the past that will be relevant to your work. So you're not starting from nowhere. You're starting from somewhere. So, you mentioned density. As you can see, perhaps, on the next slide, if you can see the kind of information that, we'll go back to that one in a second. Yeah, we'll go back to that one in a second, but if you can just, go to that one. So you can get very precise numbers representing the density of air, the density of an egg. An average density of egg is probably going to be variation. Density of salt as a possible substance you're going to test in this experiment. Now, this summary that you see on screen down in the bottom there does not have any explicit citations. So you're not told where this comes from. But if we can go back to the previous slide, you should be kind of fussy about this, about where you find information. You should write it down. Now, people do cite sources, even in everyday conversation. You maybe don't realize you're doing it, but you might say, I saw this thing on YouTube last night and they said blah, blah, blah. And so you do cite your sources now and then, but just in a scientific paper, just saying, someone once told me that Europe is bigger than Africa or something like that. I mean, that's just stupid. You're not vague. So a table like this will require you to be as specific as possible about where you got your information and what that information is. And let me tell you something that happened. This about 30 years ago now it happened, but I remember it vividly. Someone selected a bunch of papers from a scientific journal and actually looked up the papers in the reference list at the back of each scientific research paper to see if the citation was correct. And a lot of them weren't. And so that's very interesting. Even in professional science, as I say, people, are fallible, and even in professional science, people, you can misread sources. You can state something that the source actually did not say. So this is something you do have to be careful about. We want to we want to mute the fallibility of people a little bit, and being very precise and careful about where you got certain information or what that information is part of science, certainly.
Yeah, and I wonder, Greg, if now in the internet age, if this has now become a bigger problem, because you can literally just go to Google and ask these questions, and a whole list of information that's going to be right there at your fingertips. And you could just grab that information, not really being cognizant of where that information is coming from.
Yeah, I've thought, and I've said this to my classes, 40 years ago, if you thought the sky was green and the grass was blue, you're just some kook that people know. But nowadays, if you think the sky is green and the grass is blue, you can go online and find 1,000 people who think the same thing, and suddenly you're a community, and you talk about conspiracies and so on. And so it's very easy for error to be amplified. Now, again, if we contrast the past, in the past, when everything was in print, almost everything you read in print had been edited. So in other words, if it's a journal article or a newspaper article or a magazine article or a textbook, every word you read was written by somebody and then read by somebody else, and this at least one other person. And then this other person would make comments to the writer. So that's a kind of an oversight, you know, and it's certainly very more intensive in science than elsewhere. But even, magazines today, if someone writes an article for a magazine, then the magazine employs a fact checker to make sure all the facts are right. So that was a very important thing that improved the credibility of the media you were exposed to. Nowadays, of course, some science websites are excellent, very good information, but some are not, and sometimes it can be difficult to tell the difference.
Yeah, for sure.
So I don't have some magic tip to allow you to distinguish one from the other, but I do feel for people trying to make their way through a complicated scientific question, whether it's like it's vaccination or something. Getting reliable information it's very hard to know what sources are more trustworthy than others.
I think the key takeaway is just being diligent, probably. Anne-Marie, you have something to add?
Yeah, I just want to add on to that. As a science teacher in my classroom, what we usually look for, just as a baseline to have an idea, because there's so much information out there, you should be able to see a date where it was published. You should be able to find the name of the author. If you can't find the name of a person, you're going to be looking for the name of a publisher or an organization. For example, if you're looking for some information about space exploration, you might go on a NASA website. You won't necessarily find the name of that one person who wrote the page, but everything published on that website is supported by NASA itself as an organization. So that's something you can look for. So government websites are going to be like reviewed and copyright and things like that. If you cannot find any of those small information like the date of publisher, the name of the author, usually you should ask yourself, where is this coming from? Maybe I should look somewhere else. Another thing as well, try to look at something that has a somewhat neutral tone in the way that it's written. Scientific paper are going to be looking both at the good and the bad sides of an opinion or data or evidence. And you want to look at something that is not trying to just convince you that their own idea is the best and everything else is wrong. So you want to find something that has this neutral tone, and that could be a good start.
Yeah, great advice. All right, Greg, let's get to our next step, which is the hypothesis stage. Walk us through what a hypothesis is.
Okay, a hypothesis is a guess as to the answer to a question. Now, the word hypothesis is not really used in common English. In common English, sometimes we use the word theory as to refer to some kind of wild guess. I have a theory about this, I have a theory about that. It doesn't even have to be an educated guess. It could be a wild, even a ridiculous guess. In science, that's not what the word theory means. And so you have to realize sometimes words change their meaning in different disciplines. So in science, a theory is an explanation, especially a broad explanation. And it's likely to have had a lot of confirmation over the years. So it is more than a hypothesis. It's not necessarily right, but it certainly has a lot of support behind it. hypothesis doesn't necessarily have much support behind it. It might be an educated guess. You might have a good reason for thinking it. But again, the important thing about a hypothesis is that it directs experiments. It has to be fruitful. So if we look at this hypothesis, if I add things to water, then I can make an egg float because I know eggs float in salt water. So Michael, do you have any strong opinions about that if statement there?
I mean, it's very general. I think that it's a good starting point. You know, there's a lot of things that could probably go wrong in there again with the things. Well, what are things? We're going to add things to water. What exactly? It is very general, probably not specific enough.
So what about that over there on the right? How would you say yes or no to those questions? So you're saying the first one, there's definitely a yes. It's related to the question, but it doesn't provide direction.
No.
Yeah, it is a bit vague. So we might be able to define things a bit more precisely in a way that does direct our experiment. So instead of things, we specify the things. In this case, baking soda, salt, and sugar. So we're going to test each substance, dissolve them in water, and see if they make eggs float, and how much of each. We're going to put tablespoons of each substance in water, or teaspoons rather, of each substance in water. How much of each substance will have to go into the water to make eggs float? The hypothesis here is that baking soda is denser than either salt or sugar. Our background research told us that. So we're being more specific. We're guessing that baking soda will make the egg float when a lower amount is put into water. There are things that can vary in an experiment. You want to, Michael and I can go over this bit at the bottom. What are your variables? A controlled variable is a variable that you keep constant. It's just sort of contradictory. How do you keep something that varies constant? It's something that can vary, but in the limits of the experiment, you're keeping it constant. So, Michael, in this experiment, what are you trying to keep constant from treatment to treatment?
The water and the egg, essentially, and the amounts.
Yeah. So you're going to be measuring stuff. You're going to be trying to measure as fairly and precisely as possible. Manipulated variable, that's something you change. So in this case, what is the manipulated variable?
So we're going to change the amounts of sugar, baking soda that we put into each of the glasses of water.
And then the responding variable, what we observe as a consequence of our conditions.
Right. Egg floats, egg not floats, egg explodes, egg, dissolves into a different dimension.
That would be path-breaking science. Let's hope something like that happens. At this point, I'll just say that Michael's list of possibilities certainly includes some interesting ones, but good science does not just include spectacular conclusions. Good science means getting a good answer to a question. And maybe the answer is boring, maybe it's not what you want, but if it's a good answer, then it's good science. So in a way, it doesn't matter what the answer is, as long as we've done what we're supposed to do. Okay, well, Anne-Marie, would you like to talk about the method and the results?
Absolutely. Awesome. Thank you. So that was a great intro to our little project here. And I guess one thing that just popped in my head as you were talking about just having a good answer to a question, I think one thing that we have to resist as scientists or when we're doing science projects is sometimes we think that we have to have like the best, beautiful results that are going to mean so much and have these magnificent conclusions. But sometimes, you're going to design an experiment and your conclusion is going to be that nothing has changed or nothing has happened. And the goal is really going to be to try to understand why nothing has happened. Did you make a mistake while planning or doing the experiment? Or did you actually just discover that nothing was happening when you did this experiment? And that's just what your conclusion is. So don't think that if you don't get flashy, great, beautiful results at the end, it means that you failed at doing science. That's definitely not the case. So in this case, in our experiment, we've set up our variables. We have a prediction or a hypothesis of what we think is going to happen. And the first thing you need to really ask yourself is, what am I actually going to need to do this experiment? So what are all the pieces of material that I need for my method? And in the bottom right corner of the slide here, you can see the list of the material. So once again, I like to think of the method and the list of material as a recipe when you're doing something to cook or bake in your house. You want to make sure that you have a step-by-step method that has all the components that you need. And you need to make sure that your list of material has everything so that before you even sit down to do your experiment or your muffins at home, whatever you're cooking or baking, you have everything you need on the table, and you know you're not going to have halfway through your recipe to go back to the grocery store to get something because you forgot to bring it. So your material list is really important. And you want to try to make your list and your method as precise as possible so that if you had created it and you gave it to a friend, your friend could do the experiment for you without having to call you and ask questions. Okay, so you want to make sure that this is specific. So here you can see in the list at the bottom right, I need 4 glasses and 4 spoons. You need masking tape, water, measuring cup, teaspoon. You're going to need your different substances. So we have salt, baking soda, and sugar, 4 different eggs, and something that could be helpful maybe to time how much time it's going to take for the eggs to float or actually sink. So make sure you have that down. And at home right now, if you have the material ready, because some of you had received the information and the worksheets beforehand, you are welcome to follow along in a few minutes once we're going to do the demo together. So that would be your list of material there. If you go back to the upper left now, we have the method. So remember, this should be like a step-by-step that you should be able to follow one step at a time. In our case, we are going to have 4 different glasses that we are going to put different substances in. So the good part here that you have to do first is to make sure that everything is properly labeled. So it's really important when you do science. In our case, we're going to we're going to use sugar, salt, and baking soda, which are things that you could actually eat and they're not dangerous. But sometimes in experiment, you might be using chemicals, and it's really important to make sure that you label everything first so that you don't make any mistake, but also for safety reasons so that you don't mix things together that shouldn't be mixed or touched, etc. So make sure that you label your glasses. So you have 4 glasses, you can label them water, baking soda, salt, and sugar, or you could decide to do 1, 2, 3, and 4, anything that works for you to make sure that you know what goes in each of those glasses. The first treatment or condition that we're going to test is what we call our control. So earlier, Greg talked about controlled variables. Those are things that you're going to keep the same or constant throughout all of your experiment. A control, it could be a bit confusing because the words are similar, but in this case, it's a condition or a treatment that you're going to do to compare the rest of your experiment to. So we want to see if by adding something into the water, we're going to change how the eggs are floating. But to do that, we need to be able to compare it to just a glass of just water. So you're going to have your first treatment, our control, which is going to be just the water. And then we're going to have 1 glass for baking soda, 1 glass for salt, and 1 glass for sugar that we're going to be adding into the water. So you could also label your spoons to make sure that you don't mix or cross-contaminate your spoons. So that could be a source of error if you're actually using the spoon for the baking soda and by mistake you actually dip it into sugar and then you end up putting sugar into your glass that was for the baking soda. Well, then you just mixed up your results and your conclusion won't be necessarily, you won't be able to be confident in your conclusions. I'm just wondering, should we be doing the demo at this point together?
Sure. Yeah. Let's go to our special camera for my colleague Amanda, who has got our 4 glasses set up, labeled there 1, 2, 3, and 4.
Amazing. Okay, so I'm going to talk over and Amanda is going to kind of go through the experiment as we go. So what she's done already, she's labeled the glasses perfectly, number 1 to 4. So number 1 is going to be just the water. Number 2, we're going to have the water, the baking soda. Number 3 is going to be the water, and we're going to add the salt. And number 4 is going to be the water, in which we're going to add the sugar. So she's already put 250 milliliters of water to each glass. So this was one of our controlled variables. We talked about making sure we had the same amount of water. We want to try to have water from the same source, potentially also water at the same temperature. We want to make sure that everything about this water is the same between each of our treatments. Usually, if you did this at home by yourself, you could do one treatment at the time, and when you are done, do the next one. In order for you to see like all of the treatments being done, we're going to be doing them one after the other and then come back to the first one. So what we're going to do is basically add 1 teaspoon of the substance, so either the sugar, the salt, the baking soda, and then mix it into the proper jar. And once we've done that, we're going to try to put an egg into it and see if it actually floats. So before we do that, I think it would be important to actually try to put an egg in the water first to see if it actually floats.
Yes, let's put the egg into our control there. Number 1 does not float.
Okay, so number 1 sinks. So we're going to try to see then with the treatment number 2, which is our baking soda, we're going to add 1 spoon of baking soda. And we're going to make sure that we stir that pretty well. And another thing to control here, trying to stir, about the same amount to just make sure that you're consistent between each of the jars. And then we're going to put an egg and see if it actually floats.
Negative.
Negative. Okay. So at this point, like I said, if we were doing this at home and you had all the time you wanted, you could keep going with number 2 and add more, but we're going to go with number 3. So now Amanda has added some salt into the treatment number 3.
Again, negative.
Negative as well. And then we're going to add again a teaspoon to number 4 for the sugar. Mixing. And what we don't see right now is that Amanda is putting the spoons aligned with each of the jars at the back of the jar, so she doesn't mix the spoons. So we're being as controlled as we can be. She even labeled them.
Again, not floating.
Not floating. Okay. So in order to do the second tryout here, we're just going to remove the eggs for the treatment number 2, 3, and 4. And then we're going to be adding another teaspoon in each of the jar and see if the eggs are actually going to float. And the goal here is that we're actually trying to figure out really how many teaspoons of baking soda, sugar, or salt do we actually need for these eggs to float. So we're going to be doing this together until we get at least 1 egg to float.
We should also point out to Anne-Marie that we all tested this at home, and I actually tested this at home as well. And what was interesting was that, my variables were a bit different than Sarah's variables and perhaps anyone else's variables, because when I first did this experiment, all my eggs floated. And then I went through the process like, okay, that's very odd. Only with 1 teaspoon of sugar, baking soda, and sugar, they all floated. But then I realized that the variables, the eggs were not all equal, because my eggs, because I don't eat eggs, I had gotten some eggs that we use for workshops had expired. They were like 2 months old expired eggs. And so something, obviously had happened to those eggs that caused them to float rather than the ones that fresh eggs that we're using today in this experiment.
Exactly. And I think that ties back to what Greg was talking about being able to repeat scientific experiments. And so to make sure that you really have to spend a lot of time actually comparing those methods. And if you can't repeat something, you have to ask yourself, okay, did I do a mistake? Or is there something in the method that I've done differently? Or is there something acting up on this experiment that I haven't controlled properly? Mm-hmm. And it's really important to actually look at that and to have a very detailed method so that someone else can repeat it.
And this repeatability that Greg had talked about before, this is really at the heart of this method right now, is trying to figure out, you're conducting an experiment, can somebody else repeat it, and using those steps. That's why writing down all these steps is so important.
Exactly. And we keep talking about someone else repeating it, but it's important that you can repeat it yourself as well. It's always a bit trickier for someone else to repeat it because there's going to be sometimes, slightly different jars or slightly different types of eggs or slightly different utensils and things like that could bring some variation. But you should also be repeating your experiment more than one. Ooh, we have an egg that floats. So that is number 3. So that's our condition number 3. So that's the water and the salt. Amanda, how many teaspoons did you end up putting in? 3. Amazing. So after 3 teaspoons, the egg in the salt was floating. So at that point, together, we're going to go back to the slide to see how we actually collect the results from this. But at home, after the workshop, you are encouraged to actually keep doing that with the other substances as well to see how many teaspoons you're actually going to need to make sure that those eggs can eventually float. Potentially, you're going to get different results for each of those substances because they are all different. And then you can see here, we've actually we've done the experiment before this workshop. So we were just doing it again with you now to show you how to do it. But these are the results that have been obtained in the past. So if you look now, we have what we called the data that we collect from this experiment. So these are our results. And again, I talked earlier about the importance of having a list of material and a method that someone else could understand if they looked at it. It's also important to organize your information and your results in a way that someone else could look at and quickly understand what the results are about. So in this case, we have what we call trials. So I said it was really important that I could do this experiment more than once and compare my results together. That's what we call a trial. So if I do the same experiment 3 times, I would say that I have made 3 trials of the same experiment. In this case, the 3 data table that you're seeing on the left correspond to 3 different trials. So Amanda, before this workshop, has done this experiment 3 full times with a different set of jars, water, and different sets of eggs. And she has written down for each how many tablespoons she added for the baking soda, the table salt, and the sugar before she got the egg to float. So you see that there's important parts in there. The first portion at the top is the title. You want to make sure that you have a descriptive title that tells you what's in the data table. So we have the amount of solute needed to make an egg float in 250 milliliters of water. Now you have at the top in the darker orange section, the labels. It's the type of solute, which is basically no solute. We didn't add anything to the water, the baking soda, table salt, and the sugar. And then you have the number of teaspoons of solute added. For the water or the control, we didn't add any. So it actually floated right away. And then we could also have put 0 in that box there because basically we were, no, sorry, I shouldn't say that. The egg didn't actually float because we didn't add anything. So it would be nothing. And then the baking soda took 6 teaspoons. The table salt took 4 in the previous trial that we have done. Today it took only 3. So we have a bit of a difference here, which we can talk about later. And then the sugar took 11. So that took a lot more. And then the second trial, the table under, shows you slightly different results for the same experiment. And then you have the third trial at the bottom as well. There's also, when you're doing an experiment, you want to make observations. So observations are things that you can see during your experiment that you can note down that you think would be important. So one thing, for example, that we noticed during this experiment is that the baking soda wasn't dissolving very well in the water compared to the salt and the sugar. So that's something to note because it acted a bit differently from the other substances that we tested. So that's something to keep in mind and that we could maybe discuss later in our results. Yeah, I think that was it for that slide. Just checking if I forgot anything that I really wanted to say. The other thing that I just want to mention quickly here before going into the second part, you can stay on the next slide. The importance also of doing multiple trials is because if I do it only once, I don't really know if my results are correct. So I've done my experiment once. Let's say that it took me 3 tablespoons to float the egg with the salt. well, I don't really know if it was luck. I'm not quite sure if I put the right amount of salt every teaspoon or if I put too much or not enough. So I want to do it again to make sure that it's correct. If I do it twice, maybe once I'm going to get 3 teaspoons to float the egg, and maybe the second time I'm going to get 7. So if I've done it only twice, well, how do I know which one is actually correct? Like, did I make a mistake the first time or the second time? So 2 trials is not enough to really feel confident that our results are correct. So that's why we do at least 3. And you hope, technically, if you're doing it pretty well, with 3 trials, you're hoping that at least 2 of your trials are somewhat close together. And maybe the third one might be a bit far out, but if the other 2s are very similar, then you can say, there's a higher likelihood that those 2 that are similar are correct than the third one. And then your job is going to be to figure out, why is the third one not closer? And maybe sometimes all of your trials are going to be very similar, which is great, which is what you want. If you don't have trials that are close together, you want to try to figure out why. So once you have your results, you want to prepare them and organize the data to present it in a visual form that's going to be easier to read and to present. So the good thing with the trials is you can actually calculate the average or the mean of the values of the 3 trials together. So in our data, for example, for treatment number 2, and I'm just going to go over treatment number 2 in this case, we had the first time we did it, we measured 6 teaspoons, the second time 8, and the third time we measured 6. So you can do the average. So you add the values of each trials together, and you divide that by the number of trials you've done. So in this case, we're going to divide by 3. And in this example for the treatment number 2, which was the baking soda, it shows that we needed an average of 6.67 teaspoons of baking soda for the egg to float. And you do that with all of your conditions or each of your treatments. And then you can put that information into a graph to be able to use this graph to make your conclusions. So the graph, similar to the data table, is going to need some basic information on it to make sure that someone else could look at the graph and understand what it's about. The first thing you should see up there is a title, descriptive title that tells you what's in the graph. So average amount of solute added in teaspoon to make an egg float in 250 milliliters of water. It's really clear. Then you need to make sure that you have your both axes have a label and units if it's the case in your experiment and you have a unit to put there. So on the x-axis, which is the vertical axis there, is the number of teaspoons that were added to the water. And on the x-axis at the bottom, that's the type of solute. So in this case, we have a bar graph that has 3 bars. You have the baking soda, the table salt, and the sugar. So one thing I always tell my student, when you look at the news, a lot of the time they're putting some graph up there and they'll be like, ooh, science says that this is happening. And you don't even have units on those graphs. You don't even have a title, you don't even have a source. It could be a graph from we don't know where. So make sure that when you're looking at data or information or when you're creating those graphs, you want to make sure that someone else can look at it and have the information that you need to critically analyze this data and see if it actually makes sense.
I guess that's sort of the offshoot of going through and understanding the scientific method, is that not only it makes you a better scientist, but it also makes you a little bit more critically minded as you're looking at science that you're reading. When you're seeing things on websites, you're seeing things on TV, like these graphs and whatnot, like you said, Anne-Marie.
Exactly. And I think that's why a lot of the time scientists are very, I don't know if I can say critical, or that probably isn't the right term that I'm looking for, but we tend to look at data or informations in the news and the media with a very critical thinking aspect to it, because we're thinking, you know what, if I actually did this graph and tried to publish my data with this graph, it wouldn't go through because there's not enough information for anybody else to actually verify that my data and my information is correct. So you want to really make sure that all of this information is added. And that way it gives confidence to the people actually looking at the results and the conclusion that this has been done in a proper way, which ties back to what Greg was saying about how the method is often more interesting than the results themselves, because you want to make sure that the method has been planned and done properly.
Right. So, Anne-Marie, we've got a little bit more to finish off with scientific method, but I just wanted to point out we've got about 10 minutes left. So for anyone that has been watching and has some questions, you can put them into the chat. We'll definitely want to answer all your questions. I already had one coming directly to me, so I'll have time to answer that. But if you just want to ask on camera, you can raise your hand and we can you can unmute yourself. You can just go down to the reactions there and just raise your hand, and we'll see that you'd like to ask a question about the scientific method before we end off today. So let's finish off with some of our conclusions, Anne-Marie.
Awesome. So as you said before, there's going to be a full workshop on the analysis of the results later this year. So please tune in for that later if you really want to have more details about that. But basically, once you've done your graph and your average calculations, if your project is a bit more complex, you might have additional calculations, more graph. That's totally great. But if you might have a simple experiment also and have just one graph, which is also great. So you're going to basically try to interpret your information. So you're going to take your graph and think of it this way. If you had to summarize to a friend the important information shown on your graph and those results, what would you tell them? So look at the different conditions or treatments that you've tested. What are the key summary conclusions for each of these things? So in our case, for example, well, the egg is not floating in 250 milliliters of plain water. And then, for example, the egg floats in 250 milliliters of plain water with an average of 10.67 teaspoons of sugar mixed in. So when you're doing your interpretation or conclusion, use the specific values and the numbers that you have calculated to support your conclusion. You did all these great calculations, use those numbers to use as your evidence to support that.
Wonderful. We've got a couple questions that have come in, and some really good questions, actually, because we have just walked you all through an experiment, which, of course, is not the only kind of science fair project that you may be working on. And the two questions are actually both related. If somebody was working on an innovation or if somebody was working on a study, how would the scientific method change in either of those variables? If you want to maybe throw back to Greg to answer that, maybe Anne-Marie, you can comment on it.
Sure. Well, I'll talk about innovation. Innovation, you're making something that presumably can do something that is not possible at the moment. So you're coming up with some new way to do something. Certainly, that requires things like creativity and just mechanical skill, perhaps. But so that's, I mean, there's no method to that. I mean, how good is your imagination? It's hard to give rules for the operation of human creativity. But to see if your innovation is of value, to see if it works, then you would be using the scientific method. So you're going to be performing an experiment, some kind of experiment, to see if your innovation actually works. And when you're doing that, you're observing all the procedures that we've mentioned here. You're trying to be fair, and you're trying to, you have several constant variables, and you're looking for some response. And so a lot of what we've said about the scientific method in terms of an experiment applies to an innovation, except that up front, you're, it's a bit less specifiable in terms of steps. But certainly, I know in the past, some students in science fairs have come up with innovation simply because, in everyday life, they say, oh, I wonder if there's a better way to do that. And, they start thinking about, as we did, they start thinking about ordinary events they see every day. And that's where it starts.
So still starting with a simple question, can still find some really fascinating results.
Yeah. Maybe Anne-Marie can say a few words about a study.
Yeah,
I think for studies, it's always a bit tricky. The idea with studies is that you would be taking data that has been collected by someone else, and then you would collect a large amount of data, maybe on slightly different conditions or a different situation, and you would do your own analysis of that data. So you could be comparing different studies together to see how they relate together, or if they're very similar or very different. So the studies are really going to be based on lots of research that you're going to do from previous research. So a lot of background information there. And then you're going to have a lot of maths and lots of analysis that's going to be done. And you're not going to have really lots of necessarily hands-on material that you're going to manipulate. So it's a very different types of project, but it's also very important because sometimes you might already have all the background information and the work has been done. It just hasn't been necessarily analyzed in the way that you thought about that question. So you're adding a bit of a step to it. So really you still have a hypothesis, you still have a prediction, you still have some variables that you're going to compare and test together, but you're not going to go through that experiment phase or innovation phase, where you're still going to have your analysis, your conclusion, what didn't go well, etc. But it's just done a slightly different way.
If I can add something, Anne-Marie, in the last couple of decades, there's been a branch of science that has really exploded, and that's called meta-analysis. And that's what Anne-Marie was talking about. That let's suppose you have a number, maybe you have 150 trials of a certain heart medication. And these were done by different people at different times with different people. Is it possible to somehow meld all these results and derive one conclusion from them? And that's not a trivial task. I mean, it can be very difficult, but if you want a key word for doing a study, look up meta-analysis, and that will acquaint you with the fact that a lot of like especially medical results that percolate into the media are the result of meta-analyses of many different studies that are kind of hard to compare, but there are methods that exist to do that now.
And of course, when you say meta, Greg, you're not talking about the new Facebook group, right?
No, nothing that sinister.
So Anne-Marie, just as we're ending off here, one thing that, of course, we didn't get to today, but we're going to focus on for a whole other workshop, which all of these, the scientific methods, if you're doing experiment, an innovation, or a study, would have to go through an ethics and safety review. And that is actually going to be the next focus of our next workshop on December 7th. Did you want to say a few words just about that as a preview for that?
Yeah, so for safety, if you're working with any type of chemical or any type of objects that could be like dangerous to you or other people, just double check maybe with an adult, especially for a science fair project, especially a science teacher. It could be great, especially if you're using like chemicals and things like that. There might be some restrictions that you need to follow. If your project at any point involves the participation of humans or animal, you must get an ethical approval from your science fair committee where you're planning on doing the science fair. It's really important. Most of the committees are going to be happy to receive your ideas even before you start your project, and they're going to guide you and let you know if you can do this type of projects or not. It's not something that we're being picky about. This is an actual law in Canada that all scientific experiment must be reviewed, and there are some restrictions that must be followed. So just double check with your science fair local committee, and they're going to be happy to guide you. And there is some forms that you can fill that are going to explain to you what you can do and what you cannot do. And unfortunately, if you don't follow those steps, and that's going to be covered in the next workshop, but some projects may be disqualified by not following those regulations. So it's really important to look into for humans and animal participations for a project.
And if I can add, if you go further into this issue, you will probably be surprised about what is considered ethically out of bounds. You might have something in mind that sounds perfectly okay to you, but it turns out it's not. So you shouldn't think that you have to be evil in your heart to undertake an unethical experiment. That's not true. Sometimes it's just ignorance.
And of course, we've only briefly mentioned it at the end of this workshop, but that's why we're dedicating a whole other next workshop. So check for that. You'll probably get some invitations in your email inbox. But if you go to the website, sciencefairs.ca, you will see December 7th, Understanding Ethics and Safety is going to be our next workshop. Going to be a really exciting one. I'll be there hosting. As well, our financial aid program is now open. So if you're out there and if you're looking for some funding, check that out. That is now open to all participants in British Columbia and the Yukon. Sciencefairs.ca again, as well. Our mentorship program, that is going to be opening on December 1st. So you'll be able to work with the mentor, and they'll be, if you have some further questions, they'll be able to guide you along in whatever step you are in your science fair. Well, folks, that's the end of our hour. Thank you all so much for joining. Thank you, Anne-Marie and Greg, for joining us, for walking us through the scientific method. For all of you out there, hopefully you can check us out on our website, but also the Let's Innovate podcast, which the new season is going to be coming out, where I'm going to be interviewing past science fair participants. Really fun conversations. You can find that on any of your podcast platforms. And if you like it, write us a review or a rating. Until next time, folks, take care.
Thank you. Bye.